So now you see that you, as I was saying that this for a so when Y is a quasi affine, you can talk about OY of U. So for every U, you can talk about regular functions on U. Right, where U is any open subset. So this forms a sheaf. Now you can ask what is now the okay, function field. What is KY? Right. Or more general, okay, let's talk first about what is a stock at Fy. So take P a point in Y, then you define what is called OYP. So this is nothing but direct limit of the OY of U. P belongs to U. Right. And you can talk about the function field KY. This is nothing but the direct limit of U, OY of U. Right. So what is, so a point here, it's called germ of a function. So here it's an equivalence class. So when you think as a point here, so a point means a open subset U and a function, a regular function on U. But again, there is some equivalence relation that UF is same as U prime F prime. If you have some V which is in, of course, P and U, P contain P is on inside U and U prime. If there is some such that F restricted to V is same as F prime restricted to V. This is equivalence relation, right? So element and the equivalence class is an element of this OYP. That's how it is defined, right? This is called germ of a function F, germ of a regular function. So it's not a regular function, but it's a equivalence class. Similarly, you can define KY. So U is open in X or Y. So because if you take some function U comma F, you can define U comma F inverse in the very. So this is nothing but U minus. You take the zero set of F. Since if F is not, if F does not vanish over whole U, then there is, it is a closed subset. So U minus VF is a open subset. So you consider 1 by F. And you check that this is well defined. You take the equivalence class and this is well defined. And the multiplication is this. If you take UF, so addition is first this. So this will be U intersection V F plus G. And this will intersect because you are in quasi-affine situation, open subset of some irreducible, so which is irreducible, and the multiplication is defined like this. So if you will see that UF times V, U minus ZF F inverse. This is nothing but on U intersect on U minus ZF. This is 1, right? But this is same as this open subset in Y, right? So this is same as Y on 1, right? That's how the
product union features.
Huh? Union? It should be defined, right? So you have to take intersection. And they will intersect because you are in quasi-affine varieties. Open subset. Or two open subset always intersect. in an affine variety. So U intersection V is always
Y equal to that y comma 1. It's y the equal.
because why? What is equivalence class? Equivalence class is that y comma y comma 1 is sorry, this is equivalent to u minus zf comma 1 because u minus zf is the open subset in y. See, u comma f is equivalent to v comma g if there is a smaller open subset where f restricted to the smaller open subset is same as g. So, but this is always open subset here. So here it is 1, so that will say that. So the identity element is this. In a field, you have to give an identity element. So this is the identity element, and 0 is the additive identity. So this makes the function field. So this ky is and this is commutative because you are over the right. So this is a field. So birational classification actually of varieties are basically the study of this. So x and y are birational. Is their function fields. So these are this ky is called function field. We will see this ky birational means on an open subset if they are isomorphic. If there is a isomorphism, then their function fields are isomorphic and vice versa. So birational classification of affine varieties. So they are almost like field theory, field classification. Okay. Okay. When we do birationality, we'll come to.
The KY is same as like taking like rational functions from the body scale.
Yeah. KY.
Yeah.
Huh.
Because
Yes. Yeah. I will come to that. The next theorem will tell that. So what he's saying that so assume so for time being so assume y is affine. That means it's a closed subset in AN. So then following are equivalent. So this is a theorem. So this is important. 1. So the coordinate ring. So affine means it is inside some A and K, right? So KY is isomorphic to OY. So you define regular functions locally, right? The way you define regular functions at a point, you define at a point, and then you said that forms a K algebra, and Ky is also a K algebra, which is nothing but Kx1, x2, xn modulo Iy, and Iy is a prime ideal here in this case because y is affine. Point is that they are isomorphic. So you can see abstractly like this. For a affine variety, you have some God-given ring, like not God-given. You are starting with some ring of K algebra, and through regular functions. See, regular functions you define in some sense that to avoid this embedding. So if you say that Ky is isomorphic to OY, the OY, so it's enough to work with regular functions. So that is the reason why functions are more important than your underlying set. You don't have to bother whether y is inside an or am. When you define regular functions, is like a more general object. Though that also you depend like a g by h where polynomial, but still it is a little bit more general. Okay. For every point p in y, that p belongs to I, and mp is so p will P will correspond to maximal ideal, algebraically closed field, Hilbert-Nolsden search in KY, in the coordinate ring, right? I'll see, because now the function field I am denoting it by KY. From now onwards, sometime I'll write this as AY, associated ring. Because sometimes this first bracket and second bracket may get confused. When I am using this notation K round bracket Y, I will mostly use A square bracket Y to denote the coordinate ring. Now the point is that the imp is a maximal ideal. So you can talk about the localization of AY at MP. And OY, so by the way, whether I said, I don't remember, that OYP, or what was the notation? Not this. This was the notation, right? OYP. So this is the germ at a point. This is a local ring. This is a local ring. You can easily see that what are the what is the maximal ideal? All those equivalence class has a f of p equal to 0. This is a local ring, and these two local rings are isomorphic. This is the germ at P, or stock at P.
OYP is what?
OYP is, I just defined. No? Germ at P. That equivalence class, that if U comma F, where the equivalence class of functions. So,
Also look in and open about
Yeah.
equal.
Where P belongs to U.
Yeah.
So the point is that that is another local ring that cannot naturally define. But these two rings are isomorphic. Oh, sorry, this is 2. Now the third thing is that now this is Y is affine. So AY is a domain. So whenever it is a domain, you can talk about the quotient field of AY. And quotient field of AY is isomorphic to KY, yes. The function field of Y. So you see that when you define an affine variety, it's like embedding Y is some A and K. All the information you are getting in terms of regular functions. Right? If we assume the theorem that maps of affine varieties are maps of finitely generated K algebras, so that K algebra, everything you are getting from the regular functions. So regular functions are they are the more important. They are like, and that also gives a morphism between varieties. All right. Okay. So the proof is first of all, if you take something in AY, AY means it's a polynomial which vanishes. So AY is some quotient of say kx1, x2, xn, right? Because it's in. So from AY to OY, there is a natural map, and this map is injective always. Because if you have two functions f and g, if they become same here, so that will say that they are same on y, they will be say so this is always injective, ay to oy. So this is, so any element looks like f bar and g bar, right? So if you see that f bar, this is always injective, right? Because it's after all, this is a function, yeah. So if this is injective, I want to prove something like it's isomorphism, right? The isomorphism is proved proved like this. You have this AY and you have this you localize to MP and you have this OYP. Right. Now you see that if you take this, now MP is a maximal idea. MP is the functions f in AY such that f of p is 0, right? Now this is a maximal ideal in AY. Now what and anything and if you take some function, if you take something outside this maximal ideal, then that is always a unit in AYM, right? So that will say that this map is, this will induce a map here, injective. In fact, this is isomorphism. So what I am saying that this is isomorphism. So these are so this is the step 1. So you check like this. This is step 1. Then you prove that step 2 is this. This is isomorphism for every p belongs to Y. And then now the step 3 is that, see, you know that if you have some integral domain, so this is some commutative algebra result. A is integral domain. Then A is nothing but intersection of A of M. M is maximal ideal. If you take localization A of M and take the M is a subfield of subring of quotient field of A. So intersection makes sense.
It's a step of speed.
M in the maximal ideal. If A is integral domain. Have you seen this result in commutative algebra? This is standard that if you have some, okay, let you take it as exercise. If you are not seeing, then take it as exercise. And this is true. Now, what is the point? Point is that AY, which is the coordinate ring. Now, you know this is injective in OY. Now, this is OYP. P belongs to Y. But OYP is isomorphic to AYMP. So this is intersection of AYMP. MP is in maximal ideal. But this is same as AY. See, AY to OY there is an injective map. Now OY you can write it as intersection of OYP. Right. Or you don't need this equality also. You just, because OY is always in OYP. Regular functions, they are always give a, because this is injective. Because if you have two regular functions f and g, if you have some function f and g, regular function, if fp, if you take the stock, say fp equal to gp, so then what will happen? That there is an open subset U where f and g are same. But if you have a regular function, if on an open subset if they are same on Y. That's what we proved just now. So this map is always injective. OY to OY. Right. So then this will say that this is, so this is how it is proved.
That's only true for affine.
Affine, right? Y is affine, I have assumed. Okay, maybe we will stop here. We'll continue in the next class. But the point is that, see, now from onwards, more we can talk about regular functions. Regular functions are more because next theorem what we'll see, like this theorem, this is a very important proposition. We are morphism between x to y is a morphism of regular function. If you just give maps of regular functions, it gives you a morphism of affine, quasi map between quasi affine and affine. Which is very important. And but the point is that, see, you know this, if x and y are affine, you know this is finitely united K algebras, right? Now the point is that what is this category, algebraic version of quasi-affine? Do we have some category in the, like in the case of affine, it is finitely united K algebra reduced. Whether do you have such thing? But the problem is that quasi-affines may be affine. Quasi-affine in one space may look, it may be affine in another space. The typical example is that if you take this a1 minus 0, this a1 minus 0, which is, and if you embed it into a2, like t going to t inverse, the image is closed because this is nothing but xy minus 1, and this is an isomorphism. But whereas this is also quasi-affine, this is not an affine set. This is not an affine variety. So which quasi-affine is affine and which quasi-affine is a genuine quasi-affine is a question. So that's why it's a problem. So there are, huh?
There are way we can find out.
I don't know. I don't know whether this problem can be solved or not. Which quasi-affine, if you just take the category of quasi-affine varieties, is it, can you identify with equivalent to some other category like K finally, I don't know. That's a problem. So open subset of affine variety itself is a big issue. I mean, it's, sometimes they are affine, sometimes they are not affine. So things are, quasi-affines are, you have to be careful with them. Okay. Mostly then codimension, I think some codimension argument is there that if it is codimension, I think greater than equal to 2, whatever you are leaving out, like in the case of A2, the codimension is 2. Here codimension is 1. Or then it's a genuine quasi-affine, some kind of Hartogs principle. We'll see.